Hey guys, it's Dr. Thomas. We're going to continue with drawing Lewis dot structures. I've got a few examples. These are simple Lewis dot structures that follow the octet rule. The octet rule is where all the atoms involved in the molecule are going to be trying to get up to a total of 8 valence electrons through sharing electrons forming covalent bonds. The one exception to that is that hydrogen only wants to get up to 2 to be like helium. But we'll get going. So C3H8 is our first example. So if I want to draw a structure of C3H8, I need to figure out how to connect all the atoms so that they get to the number of electrons that they want. Obviously, all the hydrogens can't be connected to one carbon. So carbon is a special element that it can form chains of carbon atoms connected to other carbon atoms. This is a very important structure in organic chemistry and in life in general. So I have 3 carbon atoms. First of all, they have to be connected to each other to form the chain. So I'm going to put a single bond between the carbons initially. If I need to, I can come back and change that and possibly form double bonds or triple bonds. But for now, I'll start with single bonds. And then I have my 8 hydrogens in the formula. The 8 hydrogens have to be distributed around the carbons, but I need to remember, since each carbon has 4 valence electrons, being in group 4, that means that they need to form 4 bonds, because 4 plus 4 gets me to my octet, which is 8. So the carbon on the left, right now it only has 1 of its electrons forming a bond. That means that the other 3 electrons still need to make bonds to get to the octet. So this carbon can hold 3 hydrogens. So I'm going to connect those. That carbon on the left is now satisfied, its octet is full. The carbon in the middle only has 2 bonds so far, so that means it needs 2 more bonds that must go to hydrogens. And then finally, the one on the right is very similar to the one on the left. It has 3 missing bonds, so I need to connect 3 hydrogens. Double checking, I had 3 carbons in the middle, I have 8 hydrogens around it. That matches up with my formula. I cannot change the atoms that are provided in the formula, or it's not the same molecule that I was supposed to draw. So that is the correct structure for C3H8. I do want to double check, whenever you draw a structure, if there are any lone pairs that should be shown, you have to put them in the structure. With carbon and hydrogen though, they tend to use all their electrons in making bonds, so they don't tend to have any lone pairs in most cases. Okay, so now we're going to move on. Another example, similar, is going to be C3H6. Okay, so if I have C3H6, this time when I finish, I have to make sure that I only use 6 hydrogens. So I'll put my 3 carbons, same way I did before. Now if I plan out, if I look at this, I know that to fill all the spots around the carbons, it took 8 hydrogens a minute ago. Nothing's changed about the carbons, but now I have 2 fewer hydrogens. So a little bit of this is trial and error. Let's just say that I initially say the 6 hydrogens, maybe they're evenly distributed where it's 2 here, 2 here, and 2 here. So if I do that, I would get a structure that looks something like that. The carbon on the ends, if it's only using 3 of its dots to make bonds, that means the 4th dot should still be there. Same thing on the other side, there should be a 4th dot there. This is not a good structure. The 2 carbons on the ends, they had 4 dots, they made 3 bonds, that only gets them up to 7. Okay, so there is no way with this structure to get the carbons up to 8. Now I have seen students who will take the 3 carbons and they'll try to bend them to make a triangle. It's not that that is impossible, it's just that we do not like for you to form what we call a cyclic or ring structure in a molecule unless you're told to do so, because that's kind of a rare and unusual thing until you get up into organic chemistry where we do see 5 and 6 membered rings forming pretty often. But in this class, we would rather you try to form a straight chain molecule unless told otherwise. So basically this arrangement of hydrogens where I do 2, 2, 2 is not going to work. Okay, that was a bad try, so I'm going to try again. what else could I do? Well, with my 3 carbons, I'm just going to start at one end and say, okay, well, this carbon, if this is a single bonded carbon, it needs 3 more hydrogens to be satisfied. I know that I don't have enough hydrogens to satisfy these 2 carbons also, and if I can't satisfy them with hydrogens, then I have to think, oh, well, maybe I need to form a double bond. So by changing the single bond to a double bond, now I'm going to continue and say, okay, now this carbon in the middle has 3 bonds around it, so it only needs 1 more hydrogen to have its octet. Carbon on the end has 2 bonds right there, so it needs 2 more hydrogens to satisfy its octet. And now, by placing that double bond, I've managed to satisfy the octet of all 3 carbons with only 6 hydrogens. So that works out. That's my structure that I need. Keep going and do a couple more. The next one I have is acetic acid. Now we've learned acetic acid. Some of you learned C2H3O2. Some of you might have even seen C2H4O2. But the best way to write this formula is actually CH3COOH. If I have that formula, which is called a condensed formula, that's the one that's going to lead me to the structure that I need. Using one of a regular chemical formula, there are a lot of different structures that I could draw from this formula. And for acetic acid, there is a specific structure that I'm trying to get to. I couldn't get there easily from this, but I can get there from this structure. Okay, so again, I'm going to start a condensed structure. Basically, it kind of gives you the molecule in chunks where I know the first carbon has 3 hydrogens on it. So I'm going to go ahead and start out, put my carbon, put my 3 hydrogens, and then I know the carbon has a 4th bond. Well, whenever I have multiple carbons, they usually are connected to each other. So the 4th bond of this carbon is going to connect to the 2nd carbon. This carbon now has another oxygen attached to it, and then another oxygen and a hydrogen. I don't know initially how to put those together, but I'll tell you, if you go on your own and just try different variations of how to connect things, the only way you're going to get it so that everybody has the bonds that they need, carbon wants 4 bonds. It's going to have to connect to both oxygens. If I put the hydrogen on the carbon, I won't be able to satisfy my oxygens. So what I actually end up having to do is put the hydrogen on one of the oxygens. That satisfies the hydrogen, it satisfies the oxygen, because oxygen is supposed to have 6 dots. That's why it makes 2 bonds. 6 plus 2 makes 8. But my carbon here and the oxygen up here, they're both still missing a bond. Carbon wants 4 bonds, oxygen wants 2 bonds. Whenever 2 atoms side by side are lacking bonds, that's when I might think about making a double bond or triple bond. So if I make the double bond there, now all the atoms have the bonds that they need. The last thing I need to do is go back and put in lone pairs. Oxygen's supposed to have 6 dots. 2 went into the bonds, 2 more are there, and the last 2 are there. That gives the oxygen the 6 dots he needs. This guy also needs to have 2 lone pairs, and then that is the structure for acetic acid. That's it for this video.